Hi everybody, the data structure we're going to be learning about today is the linked list. They're sweet for many reasons, but one of the biggest ones is that they're really efficient at dealing with large amounts of data, especially if the data is constantly changing. So in this video, let's find out how they pull all of that off. Now, before I go further, I should let you know that if you want a friendly yet approachable guide to learning about data structures and algorithms and topics such as linked list, check out my book, Algorithms, Absolute Beginner's Guide, available in physical bookstores and online bookstores. So pretty cool for you to take a look at that. Now, let's get back to the topic at hand, which is a linked list. If I had to describe what a linked list is, the easiest way is to kind of say they're sort of kind of like arrays, a data structure we looked at earlier. They're all about helping us store and deal with a collection of data. So we saw that we have a list of groceries: milk, eggs, cereal, salami, and juice. We saw how to represent that using an array. Let's look at how to represent that using a linked list. With an array, we create an array. We have a list of items, and each item has an index position. They're stored in and adjacent to each other. They're contiguous. That, the next item points to the highest index position, which is the next item in our array. With a linked list, we have something similar, but we don't have the concept of index positions. Instead, what we have is the idea of you have one node that stores some data, and it has a reference to the next node that stores the next amount of data. So it's not a strict order, it's purely based on what each node is pointing to. So you can see the visualization of it where you have a node and you have the arrows pointing to the next item. Now, if we take a step back and go very generic to look at the details of it, this is our linked list. We are storing some items, A, B, C, D, and E. These items are commonly known as nodes. And within that, you have two things that are very common. You have a pointer, which is the arrow that tells one node to which node to go to next. And then you have, of course, the node itself. The node, as you can imagine, is a pretty big deal. It's like the star of this particular movie. So each node is responsible for two things. Whatever data it is storing, it could be groceries, it could be the alphabets like we saw earlier, it could be complex objects, doesn't matter. They are very flexible in that. And it stores one more thing, which is a next pointer, a reference that points to the next node in our list. And nodes also can store a few more things, and the linked list itself stores some extra metadata in terms of some values that might help navigating and using it easier. We'll look at that later, especially when we look at the implementation, but we'll just defer some of that topics for right now. So if we look like one of those old school microscopic views of let's say cell architecture, for example, you can imagine that a node looks a little bit like this. You have the node, and then you have the big region, which is the value and data, and then you have the next pointer, which refers to the next node. And we'll see why that I'm harping in on this a little bit. So the best way to understand linked lists is to kind of look at how they're used for common data operations, especially involving lists of information. Let's start at the top. Let's start with creating a linked list. When you create a linked list, let's say we start with node A. It's a node, and you can see that we have a next pointer, the arrow, but it's dotted in that we know it exists, but it's not really pointing to anything. There is no next node to think about. And now we create, in the next row, you can see that we now have a node called B, in which case, once the B node has been added, the next node on A, the previous node, is now solid. It means it's pointing to B because now we know there's a definitive next node to take the code through. But the next node for B, it's undefined. It's dotted because we don't know what it is. Similarly, you can see how adding each node makes each previous node's next pointer more filled. I kind of jumped the gun to the next line here. And you can see how the last node is always left as undefined. It exists, but what it's pointing to, no one knows because there's no node that it's pointing to. And so from there, you can kind of see how a lot of the operations start to build from it. Let's say we want to find a particular node in our linked list. The way we do that is we start at the beginning of our linked list. We always start at the beginning of our linked list, and we go through each item one by one, and we keep going until we hit the end of our list. And to often make this a little easier, you'll often see linked list implementations store some data around what is the first or head node and what is the last or the tail node. This is information they always keep up to date just to make it easier for us to know when to stop looking for something if you hit the end of the list, for example, and where to start looking for things, especially when you look at linked list variations where the beginning and end isn't actually very clearly defined. And so finding an item, you go through every single item in a linked list to get to what you're looking for. And you can see adding builds on top of that. We saw a little bit of adding, how it works under creating. So if we're adding an item to the very end of our list, like we did for, you start with A and you keep adding each letter, you can see how the last or tail node is initially undefined. And then as we add a node, it becomes more clearly defined, and you can see how it closes the loop here. Not all the time, you'll be adding an item to the end of a linked list. You may be adding some items to the middle of it. In this case, for example, we have a node called Q, and we want to insert it right in between C and D. And the main work here is not to go and rearrange every single node or every subsequent node like we would do with an array when we try to insert something in the middle. All we really do here is make a few operations, and all those operations involve modifying the next pointer on the nodes that are currently being impacted. So in this case, because we're adding a node in between C and D, and C has a next pointer, the first thing we do is tell C that, you know, your next pointer is no longer going to be pointing to D. Let's temporarily clear it, and let's have it point to the Q node instead. And so in this case, C now points to the Q node, and then we tell the Q node's next pointer to point to D. And that is all that is involved for a linked list where we're adding an item to the middle of an array. And you can see how this is different from what, this array, when we're adding an item to the middle of our linked list. And you can see how this is different from an array because all we did was modify the C node and the inserted Q node. DE and any subsequent node that follows our linked list has no impact from an item being added in the middle. From a performance point of view, you can kind of see how that is pretty nice. And deleting works in a very similar way. So let's say we're deleting an item in the middle, like let's say it's D node, that is in between C and E. The primary work here is to update the next pointer on C to just point directly to E. Essentially, we just, whatever link existed between the nodes in the linked list and the node we want to delete, in this case the D, we break that link and we just skip it completely. So at this point, it's an island. It just has no direct connection to the mainland, which is its linked list. And the operating system or the memory manager will clear D out whenever it realizes it. But from our code's point of view, you go from A, B, C, and then go directly to E. And based on everything I described, the performance of how our linked list works might be kind of getting clear. You know, on average and in worst case, it's always linear because for any operation, we start at the beginning of our linked list and we go until we find the node whose operation we want to perform something on. So it could be that it could be the beginning of the list, could be the end of the list, but on average, it's always linear. So searching is linear, adding and inserting is linear, deleting is also a linear task, but it's consistently a linear task. So you won't get any edge cases where things will be extremely slow on a consistent basis. Now, there are times when you have a better knowledge of the data that you're dealing with where you may not want to always start at the beginning of your linked list and cycle through every item until you want to perform an operation at your destination. And so there's some variations of linked lists that you should familiarize yourself with. The linked list variation we've been seeing so far is a singly linked list. You have one pointer that points to the next item in our node. Then you have doubly linked lists where a node contains both a pointer to its next item and a pointer to its previous item. So you can actually think of it as like, instead of having a one-way street, you now have a two-way street that you can navigate through. And another variation is a circular linked list. Imagine you're playing a game where you start with one player and the game just keeps going in circles over and over again. A common example is a card game where you have the beginning player, but there is no real end of it. So you just start, when you reach the end of the list, you go back to the beginning. It's known as a circular linked list, which is a very common implementation as well. Skip lists, another optimization also where you have categorization where you might, let's say you're playing a dictionary, you might have a skip list where your top category is the actual letters of the alphabet, and the subsequent category could be the actual words in each letter. And you can see this kind of breakdown available here. So there you have it, a very quick overview of linked lists. If you have any questions, post in the forums. Happy to help you out. The community will be happy to help you out as well. And to also keep up to speed on not just topics around linked lists, but on all the content I create. More links to resources you can follow below. And with that, I will see you all next time.